Okay, this is 10.1, first problem. Wants us to find the average velocity for a time period beginning at t equals 3 and lasting in the first one 0.01 seconds. So what we need to do basically to find average velocity, that's the slope between the 2 points. So when you plug in 3, you're going to want to plug in 3 here, you get approximately 3.86, and then you want to plug in 3.01, which gives you approximately 3.896. Now I didn't round either of those in my calculator, so I kept those in the calculator, and I'm just going to do slope. So with these numbers in your calculator, you just want to grab the y2 and subtract the y1, and then you want to divide by the difference of 3 and 3.01, which is 0.01. So basically you just do slope. 3.87 is what we get, and I put that here. So just do slope, y2 minus y1 over x2 minus x1 for these points. For the second one, I'll do 3 and 3.005. So I'll take a look at that. I'll redo this number and use slope again. I know it's kind of a lot of work to get through these four, but then for the last one, when it wants the instantaneous velocity, that's the derivative of this thing, and you plug in 3. Now, I'm going to do the power rule. So the power rule is when I multiply 3 down in front and lower the exponent on the exponent here, that's the derivative of the function. And now what I want to do is plug in 3, so now I can just plug in 3 here. So when I do that in my calculator, 3 squared times 3/7, that gives me about 3.857. Now we'll go over the power rule again and how we get a derivative easily, the shortcut basically. But I also want to go over the definition of derivative real quick. Now this is a hard one to do with the definition of derivative, but here's the definition of the derivative. The limit as h approaches 0 of this right here, it just comes from slope like we did in the notes. So if I substitute in f of x plus h is right here, minus f of x is right here, all over h. Now if I FOIL this out right here, I kind of showed my work right there to FOIL that out, you end up getting this big long thing right here. So I meant to write the limit as h approaches 0 of this whole thing is now my answer, or simplified. Now if I combine the fractions, this cancels with this, and I'm left with this up here, right here. Now dividing by h is the same as multiplying by 1 over h, so I'm just going to multiply the whole thing by 1 over h, put the h here. And then I'm going to factor out an h from the top here, so that it gets rid of these h's here, gets rid of one of these h's, one of these, and one of these. And then I can cancel this h here. Now I can take the limit as h approaches 0 of this thing here. It's just going to be x squared, 3x squared, because these two add together. And then these terms all go to 0. And then there's still 7 in the bottom. So when I evaluated the limit, I got this as my derivative. So that's exactly what we got when we use the power rule up here. I switched to x for some reason, but it's supposed to be a t. But you get the idea. There's the derivative using the definition of derivative, which is a lot of algebra and a lot harder. The power rule is going to be a shortcut, but I do want to make sure you know how to use the definition of derivative as well. And the last thing I want to show you real quick is alpha window. You can take a numerical derivative. That's taking the derivative at a certain point, which in this case we're doing the derivative at 3. So we're going to do the derivative in terms of x of our function. We're going to use x instead of t here. Our function is x cubed divided by 7. And we're going to do that derivative at x equals 3. And that will give us our answer as well, 3.857. Okay, the next problem gives us the cost equation in dollars of producing x units right here. And it wants us to find the average rate of change for producing 100 units and 105. So plug in 100, you get 12,800. Plug in 105, you get 13,685. And just do the slope. So you're going to do y2 minus y1 over x2 minus x1. And when I do that, I get 177 here. The average rate of change. Obviously, you're going to do the same thing for part 2. And then part 3, or this last part here, the instantaneous rate of change for b. We're going to want to take the derivative of this function, which is right here. Now, I didn't use the definition of derivative. I used the power rule where you multiply the power down. So that gives you 1.6, and then you lower the exponent on that x, which is going to be x to the first now. And you do the same thing with the next term. multiply the exponent down, that gives you 13, lower the exponent on x, and it's x to the 0th, which we don't have to write. And so that's the easy way to take the derivative of a power function, of a polynomial. So that's our answer, and we're going to plug in, it says at 100. So we're going to plug in 100 right here. And that gives 173. And like I said before, the other way you can do this is pull out your calculator and do alpha window and do numerical derivative of our function in terms of x, which is our function is here, 3500 plus 13x plus 0.08x squared. And we want to find that derivative at 100. And I accidentally had 0.08 instead of 0.8, but you do get 173. All right, the next problem wants to do the same thing. It gives us the displacement of a particle moving in a straight line with an equation here, and it wants us to find the average velocity over the interval from 10 to 13. So I'm going to do slope. So I'm going to plug in 10, and I'm going to plug in 13 and get those corresponding displacement y values. And then do the slope, y2 minus y1 over x2 minus x1. I end up getting 1197 when I do that, but don't forget it wants units as well. And the units are meters per second. If we're doing the y values here are distances in meters, and the x values, when you divide y2 minus y1 over x2 minus x1, the y values meters, the x values are seconds, you get meters per second. So don't forget to enter in the units as well. Now for the instantaneous velocity, once again, we have our calculator, numerical derivative, we have the definition of derivative, and we have the power rule by hand, which is what I'm going to use. 27t squared is the derivative of this thing, which, by the way, the derivative of this would give you velocity, as we found out in part A. The slope of a distance time graph gives you velocity, and I'll explain that better in a second. But we're trying to find that at 10, so we're plugging in 10 right here. I'm sorry, this is 9. And then 10 squared is 100. 100 times 9 is 900, so it'll be 900. And then don't forget the units, meters per second. Now, to re-explain this, you have a distance time graph, which in this case looks something like this. And they're asking us for the slope between points 10 and 13 for the first part, which is average velocity. And then in the second part, they're asking at 10, what's the instantaneous velocity, which is the slope of the tangent line. And then, obviously for slope, what you're getting is distance over time, rise over run. So you're getting distances in meters times in seconds. You're getting meters per second, which is the speed. So when you take the derivative of a distance time equation, you can see that you're going to get velocity here. Okay, this next problem should be pretty straightforward. It says determine the average rate of change of the function. If you make this a little bit bigger, the average rate of change is just the slope here. So you could do the slope formula, or you could just do rise over run. So this thing goes down 2 for the rise, and it runs 5, so negative 2/5. Okay, the next problem gives us this graph right here, and it wants us to find the average rate of change from 0 to 2. So the average rate of change from 0 to 2 is the slope of this line that connects those 2 points, which obviously is 0. The instantaneous rate of change at 1 is the slope of the tangent line at 1, which is obviously 0 for mine as well. And then it wants to choose the value at which the rate of change is positive. That'd be from 0 to 1, and the reason why is because the slope of the tangent line at all these points is positive until you get to 1, and then the slope goes negative over here. So I want a positive slope and therefore a positive rate of change, because slope is rate of change. Okay, the next question says a roast turkey is taken from the oven and its temperature is 185, and the room temperature is 75, so the temperature is going to be going down. It says estimate the rate of change of the temperature after an hour, or at an hour. So at an hour, 60 minutes right here, we're looking for the slope of that tangent line, which they've drawn in for us, which is nice. So I'm going to use these 2 points. They look close enough. The rise over run then would be down 50 degrees and over 1 hour, 60 minutes. So I'm going to do negative 5/6. The next problem, number 7, says we want to find the slope of the tangent line, so we're going to do the derivative. I'm going to use the power rule again, which gives me negative 2x. If I multiply the exponent down and lower the exponent by 1, constant goes away again. So there's my derivative. And then at negative 7, if I plug in negative 7 there, I get 14. So that's my derivative, which is also my slope of the tangent line at that point. And then if I wanted to use y equals mx plus b, I could use the point that they're giving me here. The slope is 14, the point's -7, and y is 0. I could use that to find the y-intercept. And if I do that, I get the y-intercept as 98. If I multiply this out and move it to the other side. Okay, the next problem says let p equal 4.9 times x to the 1.2. Use a graphic calculator program to find the slope of the tangent line at 3.8. So if we're going to do that, we type it in alpha window and use function derivative, which is 3, and just go ahead and fill it out, just like I did here. 4.9 times x to the 1.2, and then 3.8 goes in for x, and you'll get 7.6795 for me. So I'll keep quite a few decimal places here. Okay, the next problem wants us to consider the slope at each of these points. Let's list them in decreasing order. So the highest slope is D, because that's got the highest positive slope. Next one is E. That's a little bit less, but it's still positive. Next one is C, because that's 0. And the next one is A, because that's a negative slope. And then B is a negative slope, but it's more steep, so it's going to be the smallest number. Okay, the next problem wants us to use the limit definition of derivative to find the derivative at -1. So to do the limit definition derivative, that's the limit as h approaches 0 of f of x plus h minus f of x all over h. And that comes right, I showed you guys where that comes from. It comes right from slope. So to plug this in, it's a little bit tricky. F of x plus h would be 1 over x plus h minus 3 minus f of x, which is 1 over x minus 3 all over h. And we want to take the limit of that as h approaches 0. So what's tricky is the algebra to simplify this. Now I don't know if I'll give you one this hard, but I do want you to know how to use this definition to solve some problems. I'll probably give you an easier one. But this one's tough because you can't really add these fractions unless you get a common denominator. So I have to multiply the top and the bottom of this one by x plus h minus 3, x plus h minus 3, and this one by x minus 3. So let me simplify this for you. So you get this right here if you simplify this. Now you want to distribute the negative, in which case you get this. And then the top simplifies then because x and negative x and 3 and negative 3 cancel. So you just get negative h in the top. So let me rewrite that for this right here. And then we need to divide by h. Instead of dividing by h, let's multiply by 1 over h. And then these h's will cancel. Let me rewrite that. That turns into this right here. And then I want to take the limit now as h approaches 0. So if h approaches 0, this goes to 0. And I get negative 1 over x minus 3 times x minus 3. So I've evaluated the limit now. That's my derivative. So that's my f prime of x then. But what they want us to find is f prime of -1. So I plug in -1. In this case, I get -4 in the bottom times -4, which turns into -1 over positive 16 is my answer. What's nice though is once you have the derivative, now you can just plug in with the number they're asking you to take the derivative of. Okay. The other way to do this is to pull out your calculator and find the function derivative again. So do alpha window, and it's numerical derivative 3 in terms of x of put your original function here. And that's 1 over x plus 3, and then we want to do this at -1. So we can hit enter and we can check that we get the same thing, which is -0.0625. That should be the same thing as -1 over 16. So that works perfect. You're going to see this is an approximation method, so you're going to see it's a little bit off, but that will still give you the same answer.